Yeah, this is my 10th lecture. I'm going to take up phase equilibrium. Okay, phase related operations are very common in chemical engineering. Some of the phase related operations are, for example, you take gas liquid operation. It's absorption. Absorption. This is very common in, for example, hydrogenating oil. You pass hydrogen gas to the oil. That is absorption. Then liquid is called extraction. Liquid. Yeah, extraction. Solid gas adsorption. Absorption. Vapor liquid. Okay, vapor liquid. Phase liquid. Phase relation. Phase relation. Okay. Now we are this is evaporation. Okay. Phase liquid. This is what you are using in distillation. Distillation. Vapor liquid is called distillation. Okay. So we are going to concentrate on vapor liquid equilibrium because in many petrochemical industries it is very common in chemical engineering. Vapor liquid equilibrium is very very important. So I am going to take the vapor equilibrium and try to study that thoroughly. Or this gas liquid, solid liquid, gas, you can study elsewhere. Now, for equilibrium, for example, if you have got mechanical equilibrium, pressure on the system and surrounding will be same. Similarly, thermal equilibrium means the temperature of the system and surrounding will be same. Now we have got what's called as chemical equilibrium. Chemical equilibrium. Now, chemical equilibrium. Now, what are you going to define chemical equilibrium? So, we have defined a new parameter called chemical potential. Chemical potential. Given by mu. This is nothing but your free energy per mole. Free energy per mole. So, another name of free energy per mole is chemical potential. Okay, this is written as equal to RT ln F plus theta. But this is chemical potential. F is called fugacity. Fugacity. R is gas constant, T is temperature. Theta is a function of temperature only. This is called chemical potential. This is called Lewis and Randall rule. Randall rule. So this is chemical potential. It's called Lewis and Randall rule. Now this chemical potential is used in our phase equilibrium. Okay, phase equilibrium. For example, you got a liquid phase and a vapor phase. Okay, liquid phase and vapor phase. If there is vapor here, there is liquid here. Now at equilibrium, the temperature of this phase and this phase will be same. Pressure of this phase and pressure of this phase will be same. So pressure in the vapor phase and liquid phase will be same. Pressure will be same. Then apart from that, we have got chemical equilibrium. What does it say? Suppose I call the chemical potential of the vapor phase as mu v and chemical potential of liquid phase mu l. Now, if at phase equilibrium, apart from pressure equality and temperature equality, we have got chemical potential mu l equal to mu v. That means the chemical potential of liquid phase will be equal to vapor phase. What does it mean? If one molecule of the vapor comes to liquid, another molecule go up like that. Now maintaining the equilibrium. So mu L equal to mu V. So for phase equilibrium, we have got three parameters: equality of pressure, equality of temperature, and equality of chemical potential. Now, before going further, we've got two phases here. I'm going to say two-phase system, two phase, a liquid phase and vapor phase. Vapor phase. We can have binary system, two components, ternary system, three components, etc. Now, we have seen that at chemical equilibrium, apart from temperature and pressure, the vapor phase chemical potential is equal to liquid phase. Now, suppose there are number of components, okay? There are number of components, say binary here. We got A and B. Liquid phase, A and B, vapor phase, okay? Now, at equilibrium, we have defined this as equal to RT ln F plus theta. Now, at equilibrium, the liquid phase component A will be equal to vapor phase component A. That is, the fugacity of the liquid phase and vapor phase of the component A will be same. Similarly, fugacity of liquid B, component B, and fugacity of component B in the vapor phase will be same. Because this is also another criteria. Apart from equality of chemical potential, the fugacity in liquid phase, vapor phase will be same, and this liquid phase will be same. Now, I am not going in depth into this. At low pressures, fugacity equal to pressure, F equal to P. At low pressures. See, and your distillation column, we are going to study mainly distillation. Distillation columns operate only at atmospheric pressure. Most of all distillation columns are atmospheric pressure. Atmospheric pressure is low pressure only. In that case, fugacity will be equal to pressure, and if its pressure is 1 atmosphere, it will be equal to 1. So, fugacity also has a unit of pressure, atmosphere. Therefore, at low pressures, fugacity equal to pressure. Now, with this basic understanding, let's look at the vapor phase and liquid phase. We got vapor phase and liquid phase. Now, this is vapor, this is liquid. This, of course, you can consider this vapor as a gas. What's gas? Vapor is nothing but a condensable gas. It's called vapor. So, vapor phase is a liquid phase. The vapor phase is essentially atmospheric pressure. Okay? Essentially atmospheric pressure. At atmospheric pressure, you can apply the ideal gas law. For you have got component A and component B. And for ideal gas law is what? PA equal to Na into RT by PA into V. Okay? NaRT RT. Similarly for B into PB, where PB is the partial pressure of A in the vapor phase. NB into RT. So this is the volume of the vapor phase. PA is the partial pressure of A and PB is the partial pressure of B, and RT. This is ideal gas law. Or if you know according to Dalton's law, PA plus PB equal to P. This is Dalton's law. Dalton's law says that sum of the partial pressures equal to total pressure. Okay, and PA equal to RT by V, and Na equal to PB equal to NB by V into RT. Okay, this is the Dalton's law. So vapor phase is always ideal gas. Therefore, you can easily apply ideal gas law for each component in the vapor phase. There are 10 components. Each one you can apply the component. This one, Dalton's law. Now coming to liquid phase. Now in vapor phase again, we have got ideal gas law. That is PV equal to RT. If gas is not ideal, what you do is we use the Z factor. Z is called the compression factor. For ideal gas law, Z equal to 1. If the gas behaves ideally, Z equal to 1. If Z can be greater than 1 or Z can be less than 1. If the attractive forces are very important, then Z is less than 1. If the repulsive forces between the molecules are important, then Z is greater than 1. But our case is Z is equal to 1. Compression factor is measure of deviation from ideal gas behavior. Since our vapor phase is going to be ideal gas, we would Z equal to 1 for the vapor phase. No problem at all. Now coming to liquid phase, liquid solution. See here you got like A and B solution. So liquid solutions, we can apply, we got ideal solution, or some books call it perfect solution, because not to confuse with ideal gas, okay, and non-ideal solution. Non-ideal solution. This is called imperfect gas. Imperfect solution. Another name is imperfect solution. Now, for a perfect solution, okay, what is the ideal solution? We got two components A and B. A and B. This is A, this is B. Now, according to ideal solution, the force of attraction or repulsion between A and B will be of the same order. If the A and A is 1 Newton, A and B also 1 Newton. That means forces between like molecules and unlike molecules are exactly same. In that case, it is the ideal solution. For example, you take benzene, toluene, just next in the aromatic series. Similarly, for methane, ethane, next in the aromatic series. Those things always behave ideal solutions. So, this is the ideal solution. For non-ideal solutions, there will be attractive force. For example, you put water and sulfuric acid. Temperature will be heating will be there. You put potassium iodide in liquid, water, cooling will be there. Whereas the ideal solution you put, there is no change in temperature. Therefore, ideal solution is not always possible. Most of the cases it is a non-ideal solution. And for ideal solutions, we use Raoult's law. Raoult's law. So for A and B is there, then partial fraction of A is equal to XA into PA prime. See, why you have used here, we can use here PA equal to YA into P. Partial fraction of A in the vapor phase is, and PB equal to YB into P. Where YA is the mole fraction of A in the vapor phase. Y stands for vapor phase. YB is the mole fraction of B in the vapor phase. And PA plus PB equal to P. Similarly, in liquid phase, XA is the mole fraction of liquid in the liquid phase. PA is vapor pressure at the temperature. PB is equal to XB into PB prime. PB prime is nothing but a vapor pressure. PA prime and PB prime are vapor pressure at that temperature. Okay, you can use Cox plot. You got a Cox plot which gives for different temperature, vapor pressure versus temperature for many substances available in the Cox plot. Or you can use Anton equation, log B prime equal to A plus B by C plus T. Where T is the temperature, C, A, B, C are constants, and this constant A, B, and C are available for many substances in any literature. You take HALA, equilibrium thermodynamics, or this Cox plot also you can use. Now, for ideal solution, we use this. For non-ideal solution, we introduce the fact that just like Z for ideal gases, non-ideal gases, we can use for non-ideal solution, non-ideal. For non-ideal liquids, non-ideal, ideal liquid solutions, we use what is called as PA equal to gamma A XA PA prime and PB equal to gamma B XB PB prime. The gamma is called the activity coefficient. Activity coefficient. Gamma is called activity coefficient. Gamma A and gamma B. So it's a measure of deviation from ideal solution behavior. Just as Z is a measure of deviation from ideal gas behavior, gamma A and gamma B are measures of deviation from ideal solution behavior. If gamma is 1, it's an ideal solution. This gamma A and gamma B can calculate from Van Laar equation, Margulis equation. These equations relate log gamma A as some function of A, B and composition C, X. Okay. Similarly, log gamma B is equal to, it's a function of A, B and XP. These equations are available in literature. Once you know the constants A and B and C, you can calculate log gamma A and gamma B. So you can use that gamma A there and gamma B. Now at equilibrium, I told you, fugacity is same as pressure. Then we can say vapor pressure of the vapor phase, PA in vapor phase is equal to PA in liquid phase. Similarly, PB in the vapor phase is equal to PB in the liquid phase. Now we can write PA equal to, this is vapor, this is liquid. Now PA in the vapor phase is YA into P. This is equal to gamma A XA PA prime. And for this you can write YB into P is equal to gamma B XB into PB prime. And we have seen that at equilibrium this will be same because fugacity and pressure are same. So from there you can write gamma A equal to YA into P by XA into PA prime. Then gamma B equal to YB into P by XB into PB prime. Now the pressure, total pressure is known. The distillation column operates at atmospheric pressure, P is known. Where pressure in each plate the temperature will change. If you take a distillation column, pressure is same throughout. Each plate the temperature will change, T1, T2, etc. At the bottommost will be hottest because the reboil is here, topmost is the least. So once you know the temperature in different plates, we can calculate XBB prime. From the Cox plot you can get vapor pressure. The gamma B and gamma B for the substance, whatever it is, you can get it from the Van Laar equation, Margulis equation. Now based on this, you can calculate the composition XA and XB, YA and Y and X in the along the height of the column. That means you can prepare a chart of y versus x, and you will get a graph. This is your you can Metcalfe theory diagram. This is based on Metcalfe theory. With the composition y and x, prepare the Metcalfe theory diagram and design the distillation column. This is how you go in for distillation of column. You go. Next class I'll try to give some problems on this. We'll stop with this. This is the basics of. I am not giving you the inner depth into the subject, but the overall feature, how to go about, what is the ultimate design, ultimate what is the ultimate aim in equilibrium studies. You have to generate the composition of the liquid phase and vapor phase along the height of the distillation column. Once you know that, using Metcalfe diagram, you can calculate the height of the column. With this, we'll stop. We'll continue next class.